So good afternoon, everyone. So am I audible? Hello.
Yes, sir.
Okay. So we are supposed to continue with the problem sheet 5. So before that, uh, have you tried the problems? So till question 10, it was done in the last session. Please open this problem sheet 5 and then.
सर प्रॉब्लम सेट 4 का लास्ट 2 क्वेश्चंस एक बार बता दीजिए.
Problem sheet 4 का.
यस सर, वो डिस्कस नहीं हुआ था.
Just a minute. Let me open that. So meanwhile, you tell me the question. What was the question there? Hello. So can you please tell me what was the question while I am opening that sheet? Am I audible?
सॉरी सर. सर
Mm-hmm.
सर इट इज प्रॉब्लम सेट 5. सॉरी सर, प्रॉब्लम सेट 5 का
Okay.
क्वेश्चन नंबर 11.
Yeah. Okay. So, so have you tried these two problems? So yeah. So from here we actually continue from this question. Apart from this, so okay.
Sir,
So how?
question number 10C. 10C.
Which problem sheet?
Problem sheet 5.
So how you have done that?
Sir, I'm asking that.
So have you attended the
मैंने ट्राई
last?
तो किया बट सर मुझे कॉन्सेप्ट तो सर सही लग रहा है. मतलब कॉन्सेप्ट जो है मैंने यूज किया कि वो प्रोजेक्शन ऑफ वेक्टर निकालना है, बट वो सर वो क्लियर समझ में नहीं आ रहा कैसे निकालें उस वेक्टर का, क्योंकि हमें पीएक्स एग्जैक्टली नोन नहीं है ना. पीएक्स मतलब ए एंड बी एंड सी के फॉर्म में आ रहा है इन जनरल, तो भी सर हो नहीं पा रहा वो.
Okay, you send me whatever you tried, and then based upon that I can comment how to do this. But this is like discussed in the last tutorial, and here it is like you can do it by best approximation, and if you tried this A and B, then you can do this C part. You just send me the whatever you have tried, and then we will see. So for question 10, sorry 11, how you so what is your approach? So you have tried, right, for question 10, 11.
Yes, sir.
Yes, sir.
So how you are doing this? Was the question is clear to you? Okay, so we will, I mean, okay, I am going to like tell you what is the question. So here W1, W2, these are the two subspaces of this finite dimensional vector space, and in such a way that you can write V equal to W1 direction as W2, Now this F1 and F2 are two inner product given on these subspaces W1 and W2, and you have to show there exists an inner product such that this W2 equal to is the orthogonal complement of W1, and this the second condition, that is this F of this that inner product equal to the corresponding inner product for A equal to 1 and 2 for W1 and W2. So it's like one basic idea, and then you can do. So can anyone willingly to tell before I just discuss? Okay, so here what you have to do, you first have to define a function. Okay, so if you want to define an inner product on V, so what it is, this is a function from V cross V to F. Okay, and then and you have to use the given information, that is the two inner product and the two subspaces given to you. So you define a function u and v equals to is f of u1. This is v1. I'll tell you what. So, so this is f of u2 v1, f of u2 v2. This is f of u1 and v2. Okay, where your u is, I mean it is a vector of this from the vector space, and this is, you can write it as u1 and u1 and this u1 u2, and this is v as v1 v2. Where okay, so so basically what I was just trying to say, you can write this vector as u1 plus v1, and this vector v as u1. So just not to confuse with this notation, u2 plus v2, where this u1 and u2 are coming from this w1, and v1 v2 coming from this w2. Okay, you can write for any vector u, you can write it as this u1 plus v1. Okay, because this v is given to you as the direct sum in this way. Okay, so, and you have to use the given information that this f1 and f2 are two inner product spaces on this w1 and w2, and how you will use those. And of course you have to make this inner product in such a way that this is like w1 is a orthogonal complement of w2. So how you can do that? So this is easy, right? So you can make this assignment, this f of u1 v1 is equal to f1 of u1 and v1, f of u2 v2 is as f2 of u2 v2. So, and what about others? F of u2 and v1. What about this?
Zero.
We can yeah, we have to define, so we can take them as 0, because that's how you can I mean use this, I mean you ensure about this condition. So after defining this, I mean, so actually I've written this as a directly, but you can I mean verify that this f, if this is like u1 plus v1, and this is like u2 plus v2. Then using the properties of the inner product, you can write in, I mean, you can have a idea so that you can write in this way and then define accordingly. And now you can check for this equation that will this form the inner product based upon the information, which is like f1 and f2 are two inner product spaces on w1 and w2. This is easy now. This was the like main sorry. So this was the main idea. I mean, to proceed in this question. Does it I mean clear to you how to do this? So you just need to now check all the properties that all the properties that this equation one, I mean the inner product defined in this equation one, satisfied or not. Just, and it will satisfy all the two conditions that is given in the questions. So is it clear, right? So now we will move to this question 12. So does this question clear at least to you, or you have tried? So you can tell me what is your approach. So we are like V is an inner product space, okay, and this W is a subspace of V. Of course, this V is a finite dimensional. Okay, so yeah, first, so this P is a projection. So what it is? P is projection of V onto W, okay, such that the condition that P of V, norm of P of V is less than the norm of V for every vector in V. Okay, then you have to show P is the orthogonal projection. So what do you mean by an orthogonal projection? Or what, at least you tell me what do you mean by a projection? So please tell, at least though these tutorial sessions are made for, I mean, for interaction purpose, or, I mean, if we have to like tell the solution, so we can upload the solution, or we can record the meeting and then upload the recording. So right now you have to interact, then it is meaningful if it is like you interact with us. So does the question clear at least?
Sir, if P square equal to P.
What
If
is
P square
projection?
equal to P, then P is projection. If P square is P.
P star is P. No?
P square is square.
Oh, P square. Yeah. So that is fine. And what do you mean by orthogonal projection?
An orthogonal complement of the range of P is equals to null space of.
Good. So how will you, I mean, prove this? So okay, at least you have a knowledge that what to prove in this question. Okay. So to prove, sorry. Yes, you have to show that range of P, I mean the orthogonal complement of the range of P, the null space. So how to show this? How to show this? So this you have to show based upon the given information. So how will you show this? Any idea? Not, we will discuss, but before that, if anyone wants to like verify his approach or her approach, then okay. So what you have to do, just if you want to show the like range of P is an orthogonal complement of null space of P, then you have to do like for every vector W in the range space and any vector U in the null space, then you have to, this is like you have to show, this is your claim that W and U is 0. Okay, that you want to claim in order to your prove the statement. So just let B is an vector. So this proof is like it's not the usual one. You just see and let me know where do you got this or not. So this V you can write as W plus alpha U, where alpha is in the field. Okay, so we can write this V in this way. Any problem in this? You can write, okay, for every vector you can write W plus alpha U and alpha in the field. Okay, we will see why we are writing it in this form only. So but at least you can write this V as in this way. So now if you like apply a projection on this, then what it would be, this is PV PW plus alpha PU, and this is 0 because U is in the null space of P. So and PW is W, and why is it so? Because this is in the range space of P, and this P square is P because P is projection that is given, and you have to show that this is an orthogonal projection. So at least you can use this property. So till now we got this PV equal to W. Just all right. So now this is given on any vector. This inequality is given to you. Now you have to use this the given information. So now you can name this as, let's say, equation star, and from star you can write this is, let's say, this is norm of W, and this is, let's say, norm of W plus alpha U for every alpha in the field. Okay, you can do square both sides, so you can write W plus alpha U square. Okay, and now you can open this, uh, you can open this you can I mean check. So I'm writing here for you, you have to verify each and every step where this is W and U. Is that fine? Like if you open if you write this as, so to write this you can write this W plus alpha U, W plus alpha U, and then you got this. So, okay, you just do it by yourself and solve. So now from this you can cancel I mean here W norm of W square, and you can write this I mean you can take this real part this way, so it is minus of alpha bar W comma U, this is, and this is, and what it only the this thing remains here. Okay, I can write this, and this is for every alpha in F in the field. Okay, so this is for every alpha. You here you will make this scalar some particular choice which is in this way, and you will got to know why we are choosing this scalar in such a way. So you can make this, okay, because this is this inequality is true for every alpha. So here if you put this, then the above inequality, so this my sorry minus sign go away due to this. This if you put this, so this minus sign go away, and this you can write as, let's say, 2. This is 2, and yeah, this is t, and because this is like a bar of it, so you can write I mean, this u you have to use like z bar equal to this, so you can write in this way u equal to this, and so of course this is inequality, so this is t square, and this is w u square, and of course with the norm of u square. Okay, up to this is fine. Okay, so now
Yes, sir.
so now the cancel whatever you can. So here you can cancel because t is like strictly positive, so you can write t w comma u. Okay, so now again you can set, because t is like a positive number, so you can set this t as 1 upon norm of u square, because this is true for every t, right? For every t greater than 0, so you can choose this particular choice, then also this inequality holds. Okay, now after setting this, what it would be, this is w u, and this is less than equals to this w u square, because if you like put this as I mean, if you put this t equal to 1 upon norm of u square, then this is cancel out, so you can write in this way. So now, and from this you can write w comma u square is less than 0, and when can this be possible? If you use the property, because this is like when can this be possible? So of course this is w comma u equal to 0, so that is what we want to show. Let me range of p, the orthogonal projection of range of p is orthogonal to the null space of p, and p is orthogonal projection. Okay, any doubt?
सर PW इज इक्वल टू W कैसे हुआ था?
pw, because w is in the, so where the w is coming from?
रेंज ऑफ P.
Range of p, and p is what your p is, p square equal to p, that is projection, p is projection that is given, right? P is projection. Is it fine? Hello.
Yes, sir.
सर
Let him tell.
सर इससे PW इज इक्वल टू W कैसे आ रहा है मतलब?
So if p is in the range of, okay, so so is it the doubt? So does it clear to, so except you? Is it clear to any other? Any other student? How is it? How we are getting this? So p square is equal to p, that is given, and we have taken this from the range of p. So how we are getting this pw equal to w?
Sir, because P is a projection on W and W is itself in W. So
P is projection on w.
Yes, sir, now clear.
Okay. So yeah, so we have completed with this sheet now. So and for that question, the question the one student is telling, you just send me where you are. I mean, what is your, how did you try that question, and then where find it difficult. Okay, now we will. I mean, so have you tried the problem sheet 6? Hello.
yes, sir.
Mm-hmm. So just open that. Ah, so okay. So for question 1, how did you try this? And P is a linear operator, and define y t of z1 and z2 by z1 plus I z2. This is minus 2 z1 plus z2. Okay, and you have to find this T star, that is basically the adjoint of the linear operator. So can you just I mean quickly remind to everyone, or do you know that what do you mean by adjoint of a linear operator? Because that is what you're supposed to find, right? So what do you mean by adjoint of a linear operator? Please, anyone, just feel free to tell if you know.
Sir, T star is an operator on V such that TU of TU inner product with V is equals to inner product of V with T star U.
Star of P, yeah, yes, correct. This is like
U
we will.
yeah.
Mhm. So is it unique?
Yes, sir.
And do you know how to, I mean, claim this is unique?
Yes, sir, by contradiction.
Okay, okay, fine, fine. Okay, so this is like a very major definition that in every problem or in the major problems, I mean in the various problems, you will are in need of this definition. Okay, so how to this? I mean do this question, like we'll tell for this question, and you can try accordingly for the coming problems. So basically, if you take uv from the vector space, and this this you have to consider this u and t star v. Okay, this tu is given to you, and you have to find this t star basically. So if you assume this u as, let's say, z1 and z2, and v as, let's say, w1 and w2, for sake of like doing the question. So then here it is, this complex field. So you can write this as z1 z2, and this is w1 at W2. Okay, so according to this definition, you can write Z1 plus IZ2, and this is minus 2 Z1 minus Z2. Okay, and W1 and W2. And what is the inner product given to you? This question?
Standard. Standard, sir.
So standard. So over, let's say, over U and V, and the standard inner product over complex. So this is U dot V bar, and this is like so. If you just apply this definition, what it would be? This is Z2 and this is W1 bar, and minus 2 Z1 minus Z2. This is W2 bar. Okay. So you should also like do in your notebook. You can verify. So, and then if you open this, this is W1 bar and plus I times Z2 W1 bar plus, okay, so minus 2 Z1 W2 bar minus Z2 W2 bar, and you just collect basically the terms of with the Z1, so you can write W1 bar minus twice W2 bar, okay, plus term with Z2, that is I W1 bar minus W2 bar. All right. So now you can write Z1 as this as this minus 2 times W2. This is, you can write whole bar, and then Z2, this is minus I W1 minus W2 whole bar. Okay, and you can write this as Z1 Z2, and this is as W1 minus 2 W2, and minus I W1 minus W2. And now you have to use the like uniqueness of the adjoint operator. So from that you can write that T star of W1 and W2, T star W1 W2 is W1 minus twice of W2 minus I W1, sorry W2. Okay, this will be your answer.
So by matrix,
Sorry.
so by matrix representation of T, it's easy.
So please tell. I mean, of course, if you have like another way, then you can tell. What is how you're trying?
So we write first the matrix representation of T and then find T star adjoint of a matrix and then उसको फिर linear form में लिख के.
So have you done that? You just tell me how you have done it. I mean, what is the matrix representation? At least you tell. Okay, you have idea, or do you have solved the question already?
No idea.
Okay, so you just try with that idea, and you just keep in mind so how you are defining the adjoint there, and so I mean, I from here, I mean, I found that this is like so this way I tried. This is, we can apply the definition of that joint, and then you use this the uniqueness, and you can write this joint in this way directly. But if you find that easy and it does it make, if it makes sense, you can send me after solving that question, and then I can. Okay.
Yeah, just one comment here. So we have done this in the class. So basically, if you have an operator on a finite dimension inner product space, then you just choose a orthonormal basis. Take find the matrix representation of T with respect to this basis, and then we have proved that the matrix representation of adjoint of T is just the adjoint of the matrix representation of T. So that using that relation, one can find the matrix of T star, and then once you know the matrix of T star, then you can actually easily find T star itself. So using that, also it is easy to prove.
Yes.
Yes. So yes, you can do that also. So I have done in this way. Okay. So for the next question, now you can do the question 2. Or at least tell how to do this question.
So, x inner product of x comma t plus u star y we take, then it's equals to adjoint का properties t plus u of x comma y, and
Uh-huh.
then t plus u linear operator, then t of x plus u of x comma y, and then t of x comma y plus u of x comma y.
Yes, yes, I'm getting what you are want to say. Yeah, this is correct. Yeah, this is the idea. Like that's how we will going to do. So any other? Yeah, you are. Fine. So any other? How to do this? Any other student? So, okay, so what she has like tell, this is correct. So we will see how to do this. So if you take, let's say these two are so this V is an inner product space, and if you take two vectors from this V, then you can write this as, let's say, if uh, and this T and U are the two linear operators on this vector space V, then you can write T plus U, sorry, x comma T plus U star of Y. This is the definition. So Y, and using the, because since T is linear and U is linear, then T plus U is also, you can write in this way Tx, and using the property of the inner product you can write Y. Now you can take again there, so here it will become like adjoint of T, and this is, so it is like x comma U star Y. Okay, and you can write this as T star Y plus star Y. So why is it so? Using the uniqueness of adjoint operator, you can say T plus U star equal to T star plus U star. Why is it so? Hello.
Yes, sir.
So is it fine?
Yes, sir.
Okay. So can you do the like B part?
Yes, sir.
Same way, right? Then
Yes, sir.
so any problem in this view? Any other? Or if you have doubt, then we can do here. Not very difficult. It is. You can try it also. If you have not tried, then you just apply the definition of adjoint and then use the uniqueness property, then you can easily show. And how to do this? See,
Sir, similar.
similar, right?
Yes, sir.
And any difficulty for D? Okay, so we will discuss for D. You just tell. It is not very. It is also like similar. You have to use the same similar argument. But
Sir,
we
for
will
D
discuss for.
also,
Mm-hmm.
sir, x comma t of y equals to t star x comma y, and then फिर से adjoint of t star, then x comma t star star y.
So you just start.
No, sir.
Just a minute. So here you have to start with this. Let's say, and so you just consider is an operator, then you what it would be. You take this. So am I doing correct?
Yes, sir. T star
Mm-hmm.
x comma y.
So, huh. So actually, you just I mean, just verify that this adjoint, the definition of the adjoint. I mean this t star y. So we can also write this definition, this t star x comma y equal to x comma ty. I mean you have to just you need one argument and then you can use that. So here this is t star x and y. So again, if you take t star to that side, then what it would be? This is t star of star. So in by uniqueness, you can say because this is for every x and y. Okay. Any problem?
No, sir.
So moving to the next problem, that is the question 3. So have you tried this one? So T here T is a linear operator on vector space V, which is span dimensional. Now you have to show. So how to do this part A? Okay, now in space of T star is the, or these two are diagonal. So how to do this? Any idea? Just apply, use the definition. I mean, so whenever we have to show, let's say if we have a vector space and this W1 and W2, these two are subspaces, and you have to show
The
W1 is
subset.
mhm,
The subset of one another.
subset of one another. Yes, that is that. Yeah, you can do that way. But earlier, I mean, in one question, the last question of the last sheet, what we have done, I mean, we have taken, let's say. W is in the null space of T and V in the range space of T, then if we are able to show that this is 0 for every W in the null space of T star and for every V in the range space of T, then this holds, right?
Yes, sir.
So, so all we need to show if W is in the null space of T star and V in the range space of T and the inner product of W and V is 0, then we are done. Okay. So how to do this? So since V is in the range space of T, so this we can rewrite as T of V1, where V1 is in the space. Okay, and if you write this as T of V1, so what it would be? So of course this is it's in W and V, and using the adjoint, you can write this as V1, and since the W is in the null space of T star, so it is 0. Okay, so what it would be now?
0.
So you're done, right?
Yes, sir.
So any doubt? So also so since you are saying you just, I mean, you can do by the component, I mean the element wise, you take one element here and then you just try with your that argument, and we will discuss that why, I mean, we are like why it is we are not discussing in that. So can you do for D? At least using the idea of this part A, you can tell how to do this B. Or so can you tell me how to do this B part? In this, you have to show the range of T star is the orthogonal complement of null space of T.
In the similar way, we can take W an element of range of T star and P an element of null of P.
Okay.
Then T of V will be 0 and something T star of W1 will be W.
So can
So
you?
that
Mhm.
the inner product of W with V will be inner product of T star of W1 with V, and that will be inner product of W1 with T of V, and T of V is 0. So that will be inner product of W1 with 0, and that
Mhm.
will be 0.
So can you? I mean, write other two also. Only. So you, I mean, have you tried or you still have to do that? So better if you have not tried, so just do, I mean, using the ideas of this A, and you will discuss. Okay? But it is not very difficult. You just understand how we have done this part one and the last question and the last sheet. Okay. Now, question 4. So in this question 4, since this V is, let's say this is uh, this inner product space and U and W are So this matrix is defined. So with T is a
Sir,
linear operator.
sir,
Yes.
last question 3 का last two parts C and D. Uh, sir, we have proved that U equals to U orthogonal complement का complement by
Acha.
using this from a and B we can say.
So if you have done this, you are what you are saying. If you, if you use a subspace and the orthogonal complement of U, if it is U, this is you are saying,
Yes, sir.
then then you can say. If you have proof like this result, then say. But if this question comes like independent question, then you have to, either you have to show this or independent proof. Okay.
Okay, sir.
So here T is a linear operator over this vector space, and so the matrix representation of this T with respect to basis that is given with respect to the standard, is it standard basis? Yeah, standard ordered basis, that is AJK would be I to this. So there here I is that this is uh, this one. Okay, symbolically it is this I square equal to -1. Now, so can you tell me how does this matrix looks like? If you, because this matrix is given to you and you have to write this matrix, and this is 3 by 3 matrix. You just expand the entry wise. What is the value of a11 and a12? Okay, so here it is like I square, I cube, and this is I4. Okay, that's fine. And similarly, you can fill the other entries. That is this is I cube, this is I5, I6. Is it I6?
No, sir.
Sorry, sorry.
I4, I5.
Sorry. Fine. So this is I4, this is I5, and this is also 3, 1. I4, this is 5, and this is 6. And entry wise, what it would be? So this is this I, this is 1, this is I, this is 1, this is 1, and this is what it would, this is
I, sir.
not I, right? This is I
So
to the power 6.
1 I minus 1. So second column.
Mm-hmm. Second column. Okay,
So
okay, okay.
1 I
Yeah, yeah,
minus
yeah.
1.
Yeah, yeah, yeah. Nice. Okay. Right. So till now we haven't done anything. So whatever the information is given, we just interpreted in this way. So now, how to do this question? And what, at least what has been asked in this problem? You have to find a basis for the null space of T star. Basis for null space of T star. So how will you do this? There can be.
So first we find T star
Uh-huh.
and then null space of T star subspace का basis निकाल लेंगे.
Yeah. Uh, yes. You you first find the basis for, okay. You first find, just excuse me 1 minute. Sorry. Huh? Yeah. Okay. So you have told me that you first find the T star and then you find the null space of that T star. That is one way. Correct. Any other way you can do? Can you use any of the identities that you have proved in the question 3?
range of T complement.
Yes, yes. You can find the range of T and then you just find the complement. So which way, if you find easy, then you can do that. Okay, in that way you can do this problem. You just, you just verify the answers. Right now, I have not provided the answers, but solution. The approach you have to do. Okay, so this is, done. We are done with this question 4. For 5, okay, for 5, you just tell me. Actually, yeah. So can you tell me, or so what is the question 5? You just first understand what's the problem. So V is a inner product that is given, and U and W are some fixed vectors, and this T is like a operator defined in such a way. This is so T is the operator you have defined, and this U and W are fixed, and you have to define U that is given the definition of T, that is this is V comma U and this is W. So first you need to show that T is a linear operator. So okay, so T is not a linear operator. Okay. So T is not given linear. You have to show that T is linear. So is it easy? For linear operator, what you have to show this. I mean, this you need to ensure, right? Yeah, I should not use this W because this W is given. So I will use this W and V2. This is V1 and this is V2. V1 and V2 in the. So can you do it?
Yes, sir.
Is it linear? Right? It's linear. Okay.
Yes, sir.
Mhm. So now for so linearity is fine. Okay, I'm not doing linearity here. And how about this part B? How about this part B? So you have to find, describe T star. You have to find this T star. Can you just quickly, do this in your copy and tell me? You just try it with your in a notebook, because then only you can verify, or then only you can understand. Okay. So how to write T star? You just apply the definition, that definition. Okay. T of V1 V2 equal to V1 T star V2, and you just use the uniqueness theorem. Okay. So okay, I'm waiting. I'm giving you like 1 minute or 30 seconds. Can you do it? Or you can express this? Okay. So I hope that some of you got the answer. Let's verify that. So that you can write. This is W. This is V2. What it would be? This is, you can take it out in the product property, and then you can write V1. This is V1. This is W. V2. This is R. Okay. Okay. Is it fine? is V1, this is T star of V2. So this your answer is T star of V would be W V and U. Is it fine? Is that the same answer that you have got in your notebooks?
Sir,
Mhm.
sir, sir, mine is different.
So what is your answer?
Sir, T star of U equals to V comma U inner product bar U.
Please tell me again. Inner product of U.
Uh, say inner pro- no say inner not inner product.
Mhm.
Say inner product of V comma U bar into U.
V comma U. Whole bar or only U bar?
Say whole bar.
Whole bar into U. That the same thing. I mean, I have written also. I mean, you have taken U here, but I have chosen V because U and W are fixed vectors are given. Okay. Okay.
But sir, in
Uh-huh.
sir,
Uh-huh.
um, say in mine, sir, U is multiplied,
First,
but
mhm. Actually, so see, first of all, I mean, this there's no W in your answer, and also you have chosen like T star of U. So because you should choose some other vector because U and W are fixed vector that is given to you. So that makes a confusion.
okay, sir. Okay, sir.
And you, I mean, you just I mean, see this. I mean, I have written here this time. Huh? So we have started. Let's say V1, V2. These two are vectors. We have started with this in this way. So T of V1, V2. So we just have applied this T because T is defined this way because T is defined in this way. V inner product of V with U and W and where U and W are fixed. Okay. So you can write uh, this by using the definition. So you can write this V1 and U with the W. And now you can take this out because this is a let's say scalar. So you can take this out from the first quantity, and then again this is also a scalar. Then you just I mean take this inside. So but with the bar, okay, and then this is like by the uniqueness, this is your answer. Okay. This is like just we have done in the previous problems also. Okay. Just let me know. I mean, I think you have chosen this U vector. That's why you are getting something different. So how about the C part? So here this U vector is given in this way. U1 to UN and W is W1 to WN, and you have to find the matrix of T. You have to find the matrix of T with respect to the standard ordered basis, and you have to tell the rank of this matrix. This is the matrix, and you have to tell the rank of this matrix. So how you can do this? I mean, at least you can you just calculate and you tell me what is your answer. So that your calculation also verified. So actually, for if T is that linear transformation, then how will you find the matrix? V is the finite dimensional inner product space that is given, and the basis that is given to you, that is that can be standard ordered also. So if T is a linear operator on V, then this result that you have studied with respect to the inner product, you can write if let's say this is the basis. Sorry. So that's how you are calculating the matrix, right? So have you calculated this? So you just apply this definition and you see this matrix comes out to be this. You just verify. Please verify this. How we are getting this matrix? But this matrix is this. This is UN. And this is U1 W1 and this is U2 W1. Okay, and you can quickly observe this that this is basically W. This is basically uh, this is basically U W transpose. I mean, if you write this matrix as U1 UN and this is W1. So if W is like if W is let's say this is a row vector, not this is a row vector, and this is W1 to just class argument I'm giving this. So you can write this matrix as into this, I mean this U times W transpose. And how you are getting, if U and W are two, like say column vectors, and then you can write this as U1 to UN and this as a W1 to WN. Okay, and this is like UW transpose. And what is the rank of this matrix? If you have, let's say, two vectors, one is column and this is row vector, and you multiplied them, and what is the rank of such matrix? Vectors of this form. Can you tell me, I mean, can you conclude about the rank of such a matrix? So for such a matrix, I mean, you just, I mean, verify. I'm also giving you the reason, but such a matrix is of rank 1 matrix. Hello? This such a matrix are of the rank 1 matrix. Okay. And why is it so? Can you tell me? Why is the rank of such a matrix is 1? You can take. Uh-huh. Yeah. Anybody saying something?
Rank of A B is always less than मतलब minimum of rank of A comma B. मतलब rank of A B is always less than rank of A or rank of B.
Yes. Yeah.
और फिर सर वहां से U का rank 1 से कम हो जाएगा क्योंकि
See, that is also fine. I'm just giving you the slightly different argument. If you take, let's say, W, that is of course the non-zero that is given to you. So if you take the range of, if you find the range of this space UW transpose, okay. I mean, what is the range of this UW transpose? And if you let's say apply, this is your A, and if you apply W both sides, then this is like a scalar. You take this W transpose W, let's say alpha. So what it would be, this is U, and it is like a span of U. Okay. So the dimension of the range space is, the range space of A is 1, and my the rank nullity theorem, you can say this is the null space of A dimension is n minus stand. That you don't need.
The rank.
From here, yes, yes, from here you can say the rank of A is 1. Okay. So earlier the what was the argument, that is also fine. So here, I mean, that's how you can conclude. But yeah, before that you just verify. I've written this it for you, but you just verify how you are getting this matrix of this form. Okay. So yeah, we are, I mean, up with the time. So you just try with the, I mean, whatever the problems we have discussed today, you just, I mean, go through all the problems and you do by yourself. If you have any doubt anywhere, you can write us. Okay, and you just, I mean, before coming to these classes, you just try all the problems. Okay, yeah, we can meet in the, we will meet in the next tutorial. Please, you can leave. Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
And sir, please upload this recording. Sir, we can't
Okay.
find the last tutorial recording.
Yes, it is. I mean, it is recorded from my side. So I mean, whenever I record, then it is getting uploaded directly. Yeah, but it will take time because it is like more than 1 hour recording. But it is like getting uploaded.
Yes, sir. Thank you, sir.
Welcome.